All right. So all of the webwork assignments are open for full credit until May the 6th. Um, and then we also have course surveys are now live. So this is your chance to give me honest feedback on how I'm delivering the material, what you think I do good, what I could do better on, something else I don't do that you think would be helpful. Um, so there should be an email, and I think the option is also open in Canvas to do the course surveys. They do get read by more than me. Someone else in the department will see those results. Um, Also, the results from the end of semester survey are held hostage until grades are posted. So you can be honest on them and don't worry about it impacting your grade. Now, that being said, like even a professor who gets a whole bunch of bad reviews, very often they're tenured and there's not anything the department or the university can do to really sanction them besides giving them class times that nobody likes. So if you wonder why some of your professors are really bad and still have a job, that's why. Also, some of them are really bad because they've never had any training in how to teach or present. They just took really high level classes in their field of expertise, and magically that supposedly conferred upon them the ability to teach. At least that's how the university sets up qualifications for being an instructor. So questions about the course survey or webwork being open? All right. So my plan for Thursday is to have the exams to give back. Um, so they should be graded by then. I've got some extra time today to do it. I've still got at least one more person coming to take the makeup exam tomorrow. All right, so what we're looking at now is we're going to focus in on the properties of logarithms. So we got our slider for how you feeling? With a nice Rafiki quote. All right, so our logarithm rules. All of our logarithm rules are coming from properties of exponents. So when I have b to the x times b to the y, I know I can add those powers to simplify that product. So what this ends up meaning is the log of a product becomes the sum of two separate logs of each piece of the product. So log base b of xy equals log base b of x plus log base b of y. So logarithms actually turn a product into a sum. So they actually change an operation. Now, similarly, because of our division of bases with exponents where we subtract, log base b of x divided by y becomes log base b of x minus log base b of y. So product turns into plus, quotient turns into minus. Now the power rule down here, log base b of x to the y equals y times log base b of x. So this is log's whole purpose in life is to take exponents and bring them down on the line getting multiplied in front of the logarithm. So log's whole purpose is to take exponents and move them into a position that's more accessible. And the power rule really comes from the last thing on our list here. Log base b of b to the n equals n, because log base b is the inverse of the exponential. So it has to equal just n. But the previous line, log base b of b is 1. So this n times 1 is really n times log base b of b. So they all interrelate. But one of the things you have to be comfortable with in calculus is applying these log properties. So we're going to step by step practice each one, and then we're going to throw it all together and practice some crazy ones. So here's our first one. Writing a logarithmic expression as a sum of logarithms. So we have write log base 2 of 6x, comma, x is greater than 0 as a sum of logarithms. So the x is greater than 0. We're going to see that show up in a lot of these problems. And that's just a qualification to say, remember, we can't take the log of 0 and we can't take the log of negative numbers. So it's just explicitly stating the domain restriction. But otherwise, we're just going to ignore that part. So log base 2 of 6x. So that is 6 times x. So the logs take products and turn them into sums. So I'm going to have the sum of two different logs. And then the two things that are being multiplied, that's what goes into each of the logs, each into their own log. So log base 2 of 6 times x is the same as log base 2 of 6 plus log base 2 of x. All right, now we're going to take a look at the quotient rule. So log base 3 of 10 over x, and then again, another x is greater than 0 qualification. All right, so whenever we have a fraction, I think of it like the fraction bar is going to become a minus between the two logarithms. Now, when we do this, the order matters. So it's whatever's on top minus whatever's on the bottom. So log base 3 of 10 minus log base 3 of x. All right, now we're going to see the power rule in action. So log base 4 of x to the third. So when we have that exponent inside, logs take the exponent and bring it down out front of the log. So I think of this as the power down rule. So the power is in front. We still have the same base on our logarithm, and then the x on the inside. So now seeing those three little examples, it can feel like these are simple. Whack, you haven't seen the hard stuff yet. So how about if you have to do more than one rule at a time? That's what we're going to play with now. So we get questions like this. All right, so when we look at a logarithm expression like this, we need to sort through and figure out what the order of operations are. So that way, the outermost operation that's inside the logarithm, that's the first rule we're going to use. So we have to be very careful about using the rules in the correct order. So one of the ways I like to figure out the ordering of the operations is I think about picking a number and putting it in there for x, and then thinking, what would I have to crunch on the calculator to actually crunch this up and get the actual end result? So I just pick a random number like 5. So if I plugged in 5 for x, I would have 5 times the square root of 5 squared plus 1. So if I was going to calculate this one step at a time, I'd do the 5 squared first, then I'd add 1, then I'd take the square root of that result, and then I'd multiply that result by x, and then I'd take the logarithm of that. So the last step we did inside the logarithm was do the square root result times x times 5. So that means our outermost operation is a product. So I'm going to use the product rule. Product rule turns the product into a plus of two logarithms. So I'll have log base 2 of x plus log base 2 of, so that's x squared plus 1, and then I'm going to make a trade out. The square root, I'm going to write it as the 1/2 power. So I have log base 2 of x plus log base 2 of x squared plus 1 to the 1/2. Now log base 2 of x, I can't do anything else with that. But the log base 2 of x squared plus 1 has an exponent, so I can use my power down rule. So that 1/2 is going to come down out front. So now I have log base 2 of x plus 1/2 times log base 2 of x squared plus 1. Now, it's really tempting looking at this to think that the logarithm distributes across addition, but it does not. Logarithms change operations. It changed multiplication into addition. Logarithms change division into subtraction. Logarithms don't know what to do with pluses or minuses. So this is as simplified or as we can get it. So questions on how this one played out. So the square root is the same as the 1/2 power because it's the power that undoes squaring something. All right, so our next one is an example I absolutely hate because it is written so poorly. So looking at this, I've got a fraction inside a fraction. And the problem is which fraction is inside the other. And that is a very difficult thing to see, especially if you're looking at a very small screen. So this could be the natural log of the little fraction x over 18 divided by y, or this could be the natural log of x divided by the little fraction 18 over y. But there is a way to tell which one they meant, and it's very subtle, but we are literally looking for which of those fraction bars is bigger, like literally which one has more pixels. So the one between the 18 and the y is a little bit bigger than the one between the x and the 18. So that means the x over 18 is the small fraction that's inside. So first thing I'm going to do is rewrite that, but I'm going to put extra parentheses in there. Whoop. So that's the way our problem should have been written. But there is the potential that a webwork question might have a stupid fraction in a fraction like this. So that's the reason I left this problem. All right, so we're going to handle that big fraction. So that's going to turn into a minus sign. I'll have natural log of the top, where the top is x over 18, minus natural log of the bottom is just y. But now I have another fraction inside a logarithm. So I'm going to turn that into another minus. So I'll have natural log of x minus natural log of 18. And then we still have minus natural log y from the first fraction. So we had two quotient rules, fractions inside fractions, which are very convoluted. But that's how to tell the difference between the two. All right, now this one, we actually have some practice problems in webwork that look like this. Now there's two ways to tackle this mess, but let's write it down first. So the natural log of a to the negative sixth divided by b to the negative fifth, c to the ninth. So now I've got one thing on top and two things on the bottom of the fraction. Now, whenever I have a big fraction, that division is always the outermost operation. So that's the first thing we're going to deal with is that fraction. Now, if you really don't like dealing with negative exponents, you can, before you start using the log properties, move things around so the exponents become positive and then work the problem, and that will work. Most people, though, just start using the log rules right away. So that's the way I'm going to work the problem. So we will have the natural log of a to the negative sixth minus the natural log of b to the negative fifth, c to the ninth. So my first natural log a to the negative sixth, like this is already ready to use the power rule, but I like to do my power rules all in one step. So I'm going to focus on my second logarithm here. That is natural log of b to the negative fifth, c to the ninth. Now, if you ever look at a logarithm like this and you're like, you get overexcited about bringing down powers and you're like, ooh, the powers come down. And then your brain goes, wait, which power comes down? What do I do with both of those powers at the same time? If your brain is asking questions like that, it means now is not the time to do the power rule. You need to use a different rule first. So when we're still seeing multiple things with multiple exponents, it is not time for the power rule. We've got the product in there to deal with first. So this natural log of the two things being multiplied is going to be the natural log of b to the negative fifth plus the natural log of c to the ninth. And then I recopy the rest of the equation. All right. Now there is a mistake. It is a very easy mistake to make here, but what we have right now like looks reasonable, but we made a substitution. So in place of the single natural log of b to the negative fifth, c to the ninth, we traded that out for natural log of b to the negative fifth plus natural log of c to the ninth. It's a 5. So what we're missing here is parentheses. Anytime we make a substitution, we put one thing in place of another or multiple things in place of one thing. We need parentheses around it. Now, this minus sign that's in front of the parentheses That minus sign is going to distribute through. So we will have the natural log of a to the negative sixth minus the natural log of b to the negative fifth, but now it's minus the natural log of c to the ninth. Now I can bring down my power rule, my powers. So I'll have negative 6 natural log A minus negative 5 natural log of B minus 9 natural log of C. Now the only thing left to clean up is that minus negative. Now, being able to effectively apply the log rules requires practicing with the log rules. Now, I am not going to give you the log properties on the test. That's why we don't have them like printed on the page again. The whole point of this homework is to practice using those log properties so you don't have to have them in front of you anymore. Now, when you're first practicing it, especially if you're not comfortable with them, like feel free to have them there, remind yourself how they work. But as you move through the homework, you want to eventually get to the point where you don't have to look at the rules anymore. And that could mean doing extra homework just to get more practice. So questions on how this one shook out? All right, so here we had a single logarithm with a whole bunch of crazy mess inside, and we broke it apart into the sum and difference of logarithms. Slide 11 is asking us to work backwards. So I'm starting from logs that are broken apart, and I want to compress them back together. So all of the log properties we had were equations. Well, equations can be read in either direction. The left side equals the right side, but also the right side equals the left side. So I'm going to use my log properties that we were just practicing with backwards. So we start with log base A of 7 plus, whoops, getting ahead of myself, 4 times log base A of 3. So I see I've got a plus in between these two. So I know logarithms turn products into pluses. But to be able to use my plus product rule, I need it to be log of a thing plus log of a thing. And right now, I've got this extra number in front. So before I can deal with the plus, I've got to deal with the number in front. So stuff comes down in front when it's a power. So we're going to move the 4 back up as a power. So log base A of 7 stays the same, plus now we're going to write it as log base A of 3 to the 4th. Now I have log of a thing plus log of a thing, so now I can combine it together. That will become a single logarithm of the product of the two things. So 7 times 3 to the 4th. 3 to the 4th is 81. And 7 times 81 is 567. So questions on how our first condensing logarithms worked out. All right, now this next one is actually in an in-between state. So we technically have the log of 6 times x to the 5th, so there's a product there, plus the log of 3 times x to the 8th, another product. So technically, I could break this apart more, but I could also smush it together. So we really have to read the directions here, and the directions here are saying write it as a single logarithm. So as a single logarithm, I would have 6x to the 5th times 3x to the 8th inside the logarithm. So I have log of 6x to the 5th times 3x to the 8th. Of course, if I hit submit on this, I get very sad stitch. Sorry. Because now that those insides are being multiplied, I can actually multiply them. So this is 6 times x to the 5th times 3 times x to the 8th. So just a whole bunch of multiplication, so I can rearrange. So the 6 times 3 becomes 18. And then x to the 5th times x to the 8th, I'm just multiplying more x's, so that adds. So we're going to get x to the 13th. So I have log of 18x to the 13th. All right, now this one is saying I've got this log expression. Which way can I go with it? So I've got a single logarithm. So am I going to condense this or expand this? Why expand? So with 7 times x, so what usually comes in front of logs? The exponent like powers down because it's a power. Is the 7 a power of the x? No, it's being multiplied to the x. So it's not going to come outside the logarithm. It's tempting to do that. Like a lot of stuff, numbers do just come outside, but logarithms don't work quite that way. But there is a rule we can use here. But we want to focus on like which direction we're going. So I have a single logarithm. If I'm condensing logarithms, I usually have several different logs and I'm trying to get them back into one log expression. This is starting as one log, so I'm going to break it apart. Now, the way we're going to break it apart, this is 7 times x, so that's a product. So that'll become log underscore b of 7 plus log underscore b of x. So 7 times x is a product, so we split it into 2 separate logs with a plus in between. But it takes practice getting used to which log property you're using. But does it make sense why we're using the product instead of the power rule? But those are definitely like rules that people like do confuse for each other. All right, so our next one, I've got natural log of y plus natural log of z plus 2. Now, when we see z plus 2 inside a logarithm, it's really tempting to feel like the natural log would distribute through, but natural logs don't break across addition or subtraction. Natural logs change operations. If I had this, like, I don't have a lesser order operation that addition would get changed into because it's always changing a more complicated operation into a less complicated. So this can't be expanded anymore. It has to be condensed. But the basic way to see that is we've got more than one logarithm. Now this is our product rule backwards. So we're going to have, whoops, the natural log of y times z plus 2. Now notice I just typed yz and it's like, yay, you're right. And it's like, I wasn't done typing. So no, I'm not. So this slide has a typo. It should be y times z plus 2. Now we could distribute that through, but we don't have to. All right, now one more. Log base 2 of x over z. So I've only got a single logarithm. So am I going to condense this or expand it? Yep. Why? Because there's only one log, so we can't condense. Now I've got a fraction, which is a quotient, so I'm definitely using my quotient rule here. So log underscore 2 of the thing on top is x minus log underscore 2 of the thing on the bottom, whoop, wrong button, is z. So we end up with log base 2 of x minus log base 2 of z. Now, we've had all sorts of different bases show up in all those problems we were working. So it kind of begs the question, well, how do I calculate some of those logs? Because if you look on the calculator, you're not going to see like a log base 3 button. Not there. There's a log button and a natural log button. Some fancy calculators will have a log with a box so you can type in the number, but most of them don't have that because of this formula. So the change of base formula allows us to take the log with a weird base and turn it into, write it in terms of a different base logarithm. So log base b of a is the same as log base c of a divided by log base c of b, where the c is any number we want to pick. Now, typically, we pick log base 10 or natural log because those are buttons on the calculator. And in calculus, we're going to pick natural log because natural log works nicely for our derivatives. So when I'm looking at log base 3 of 81, to type that on the calculator, I could type the log of 81 divided by the log of 3, and that would give me 4. Or I could type it with natural logs. Natural log 81 divided by natural log 3. And that would also give me 4. Now note, the log of 81 is a different number from the natural log of 81. They are different decimals, just like log of 3 is different from natural log of 3. But the quotient of the two will be the same. So we can't just change the base into one other thing. We have to change it into this funky fraction. So now we're just going to practice using that change of base formula. It's all about that base. So log base 4 of 36. I'm going to start with natural log of 36, close the parentheses, divided by natural log of 4. And this gives me 2.5849, blah, blah, blah. But they said approximate to 3 decimal places, so that'll be 2.585. So log base 8 of 57, we calculate doing natural log 57 divided by natural log 8. We get 1.944. So notice log base 4 of 36, our base was smaller than what we were taking the log of. So that our answer is a number bigger than 1. In fact, if we think about our powers of 4, 4 squared is 16, 4 cubed is 64, and 36 is in between 16 and 64. So this logarithm should be something in between 2 and 3, and we did get 2.5. Log base 8 of 57. 57 is a little bit smaller than 64, where 64 is 8 squared. So our result is a little bit smaller than 2. Now, log base 9 of 8.19, now our base is bigger than what we're applying the log to. So now I'd expect to get a number smaller than 1. So I'm going to type in the natural log of 8.19 divided by the natural log of 9. I got 0.9570 So 0.957. All right, and now we've got some fractions thrown in the mix. So natural log of the 11 halves, so 11 divided by 2. And then on the bottom, it's the natural log of 6. So we got 0.9514, so 0.951. And now our last one, log of 1/7 a fraction as the base. So log base 1/7 of 4.3. So I'm going to have the natural log of 4.3 on top. And on the bottom, it'll be the natural log of 1 divided by 7. So now, because our base is smaller than 1, we actually end up with a negative number here. Negative 0.7495. So that's going to round to 0.750. Log base 9 of 8.19, it's 0.957. Now, after this, it starts moving into solving log equations. So before we do that, let's go ahead and pull up the last writing assignment. Because we have like Thursday and all next week to finish the Amplify module, and then we'll just start reviewing for the final. All right, so with our writing assignment, my first few here are condensing logarithms. So we're just zipping those back up. Then question 2 is about using the log properties to expand. And then we put some exponential and logarithm equations on here for solving. So you don't have to do that yet. This assignment isn't even due, I think, for a bit. Um, so yes, you can see all of the webwork assignments should say due May 6th now. If they don't, and you still need to go back and work on it, email me so I can go in and make sure it got updated, but I think they all got updated. All right, so our webwork problems are just practicing using the log properties, and they're all going to be mixed up. So you'll have like some condensing and some expansion, like one after the other. So this one, though, has a nice little subtle example in there. The natural log of x to the y versus the natural log of y to the x. So you have to pay attention to which one's on the bottom and which one's the power. So the natural log of x to the y is going to bring the y power down out front. So that is a, y times the natural log of x, versus c, that's our x times the natural log of y, because we have the natural log of y to the x, so the x power is down up front. And then the other two are our sum and difference, which is product versus quotient. So we know the quotient is going to turn into a difference. All right, so let me look and see if I can find some of the weird formatting ones. All right, yeah, this one's a little bit weird. So, using the properties of logarithms, decide whether each equation is true or not. So, decide if it's properly applying a log property or if it's screwing it up. So, when I have log of A divided by log of B, is that the same as log A minus log B? Is that the way our rule was set up? So I had two separate logs and then two separate logs? They are the same base, which is one of the qualifications in our rules. Like everything always has the same base. But yeah. So if I have the log of A over B where both of those are inside a single log, that turns into two logs. When I have one log over another log, this is actually the change of base setup. So log A divided by log B would be log base B of A. So yeah, that first one is false. Now our second one appears to be trying to use the product property, but that property is similar to our quotient rule. It's a single log of a product splits into two different logs. So that guy is also false. Now our third one here though, P times the natural log of A, that's my power in front. I can move that back as a power. So that setup is correct. And then when I look at number 5 here, the log of AB, that is our correctly stated product rule. So we've just got 4 and 6. So the difference is subtle between them. But in 6, when I have the log of the square root of A, I can rewrite square root as A to the 1/2. Which would then become the power comes down 1/2 log of A. So number 6 is true here. Number 4, the square root outside the natural log, I can't do anything with that. That's the natural log being raised to an exponent. A very weird situation. But that does not become a square root inside the logarithm. So I can't move outside inside this fluidly. When the logarithm changes something, like is applied to an operation, it changes the operation. All right, so then we've got this set up. So the natural log of x to the 19th times the square root of x minus 1 divided by 3x minus 3. So the directions say use the law of logarithms to rewrite the expression in a form with no logarithm of a product, quotient, or power. So that's just a real fancy way of saying like expand it. So I've got a couple things on top of a fraction divided by another thing, but overall, the outermost operation inside the logarithm is the quotient, the fraction. So I'm going to split this into natural log of x to the 19th square root of x minus 1 minus natural log of 3x minus 3. Now our natural log of x to the 19th times the square root of x minus 1, there's a times in there. So now we're going to use that product rule. So natural log of x to the 19th plus natural log of square root of x minus 1. Now I just traded out one logarithm for two logarithms. So I'm putting some parentheses around it just in case. But there's nothing to actually distribute through here. It wasn't on the bottom, so there's no minus sign, so didn't didn't have any like change, but it doesn't hurt to put the parentheses. Now, our square root of x minus 1, I'm going to trade that out for the 1/2 power. And now we've got some power down situations. So that's going to be 19 times the natural log of x plus 1/2 times the natural log of x minus 1, and then still minus the natural log of 3x minus 3. All right, now let's look at the structure of the problem and what they were wanting us to type in for the answer. So they've given us up here, they've said that the answer is some number times the natural log of x plus some number times the natural log of x minus 1 plus some number times the natural log of 3x minus 3. So we just need to fill in what are the numbers a, b, and c. So there's my A, B, and C position. So A is 19, B is 1/2, and C, there's not a number there, but this is minus. And if we look back, they wrote plus C. So I need to incorporate that minus as C, so a -1. So questions on how this one shook out, what the answers that this webwork question wants. All right, slightly different format here is problem 5. So they say rewrite the expression as a single logarithm log A. Then it says, then the function A equals, and it has a blank, and it says, note, log is not part of your answer. They're just wanting to know when you shove all of this back together, what's inside the logarithm. All right, so looking at our crazy expression here, I've got numbers all in front. So before I can start figuring out if I'm using a product or a quotient rule, I need to power up. I need to move my powers. So this will be log of x to the third power minus log of x squared plus 1 to the fourth power plus log of x minus 1 squared. Now, don't actually like do x minus 1 squared or x squared plus 1 to the fourth power. Just leave them like that. Now, technically, I could have taken the -4 and moved it up as a -4, and it would have left a plus in between these two. Either way works. I usually just move the number, and then I'll treat the minus as a quotient rule. So I've got 2 logs being subtracted, so that's going to become a single log with a fraction. I'll have the x to the third on top and the x squared plus 1 to the fourth on the bottom. So now I just got to deal with this extra log over here. That's got a plus, so this is going to become a product. So I'll have the first logarithm. Well, now I'll just have a single logarithm. So I'll have the x to the third over x squared plus 1 to the fourth, and then it's times x minus 1 squared. So now the question was, what is A? A is what's inside the logarithm. So if we type it in like this, webwork will take it. We can also clean it up just a tiny bit, not multiply anything out, but we can just write it as one fraction. So it'd be x to the third and x minus 1 squared on top, and x squared plus 1 to the fourth on the bottom. And webwork will take either of those answers. All right, so that's like all I've got for today. Did anyone have any questions from any of the old assignments? Yes, so it's going to be the same format we used in the fall, so it ends up being 17 questions, but I think it's 12 of them are multiple choice. And if you show your work, you can still get partial credit on the multiple choice if you pick the wrong answer. But you don't have to show your work. So if you can look at a problem and you're just like, oh yeah, that's the answer, that's fine. But there's like, I think five of them are free response, so you have to show your work. So 5 of the questions are going to be from chapter 6, from the exponential and logarithms. But then the rest of it is like pretty evenly split from the exams. And we do have a final exam practice. It says practice final, but it's just the final exam practice problems, and it's still going to be worth bonus points. And it's a pretty good facsimile of what's going to be on the final. There's a few questions that are like extra, but is what? Yeah, I haven't assigned it yet because I have to go in and like fix one problem on it. But it will be.